Welcome everyone. Today I am presenting our paper called the Universal Normal Embedding. In this work, we propose a unified view on two distinct areas of computer vision encoders and generative models. Now, the heart of our research is the UNE hypothesis. We propose an ideal embedding for images that has two key characteristics. It is Gaussian, and it organizes semantic information on straight lines. And we call this space the Universal Normal Embedding, or the UNE for short. We also hypothesize that layered embeddings, including vision encoders and the initial noise and diffusion models, will naturally align with this embedding, even without explicit training. Let's look at the current situation. Computer vision operates on two separate tracks. On one side, we have the generative models. They are optimized to map initial Gaussian noise to a natural image. And in constant guidance, the initial noise can be viewed as an embedding of the output image. Now, this embedding, we know nothing about it, except that it is Gaussianly distributed. On the other hand, we have vision encoders. They are optimized to map natural image to a highly semantic latent space. In addition, empirically, the model's latent spaces admit Gaussian distribution, similar to generative noise and similar to our proposed UNE from a paper cited here. Now, if our UNE hypothesis is correct, generative noise will also naturally yield linear semantic structure. So this is the opposite direction of the Gaussian distribution in vision encoders. Now, our first empirical evidence is for the Gaussian distribution in the vision encoders. Here we can see different Gaussianity tests that we did on different latent spaces. We can see that the initial diffusion noise passes at around 95% rate, which is the theoretical pass rate for ideal Gaussian. And vision encoders pass at slightly lower rate, but they are still approximately Gaussian, only slightly less Gaussian than the diffusion models. On the other hand, here we can see the results of linear classifiers on the initial noise that yields Celebay images. We extracted this noise using DDIM inversion. Charts show that the linear classifiers do only slightly worse than the vision encoders, which are known to do well in this task. Again, this is without explicitly training the diffusion models to do well in these tasks. It happened naturally. Additionally, we found that semantic attributes are rankable within the diffusion noise. We test this by taking the DDIM inverted noise of some image and finding a direction in the latent space that is associated with a semantic property, for example, smile. And if we move the inverted noise in this direction and then generate an image from the result, we can increase or decrease the amount of smile in the image without changing the rest of the image. And we can do this with many different attributes, for example, beard and etc. Now, because this space is linear, we can also perform semantic arithmetics. For example, if we take this image of a person, of a male with beard, and we try to remove the beard, the gender also changes from male to female. This is because the beard direction and the gender direction are not orthogonal, they align. So instead of moving in the beard direction, we can move in the direction that is closest to the beard direction, but is orthogonal to the gender direction. And when we do this, we can see that the beard disappears, but the gender doesn't change. Now, to propel future research, we also introduce the noise zoo dataset. We publish all the Celebay embeddings that we used in this research. It includes image encodings and DDIM inverted noise of diffusion models. It's all free to use. In conclusion, the universal normal embedding provides a concrete framework that unifies computer vision. Thank you for your time.